Good evening, everyone. Welcome to today's session on signals and systems. This is week 5, and I am Shouharda Ghosh, second year PhD scholar at electrical engineering at IIT Gandhinagar. So, we are in the course of signals and systems, and this is week 5. So let us look at the topics that have been covered in this week. So first of all, we had a brief overview of systems. So until this week, all the way from week 2 to week 4, we were discussing mostly about signals. We are talking about the signals, their spectral information, their time information, how they look in time, how do we analyze the signal in various ways in the time domain as well as the frequency domain. Now this week we go into systems which work on the signals. Then there was this discussion on linearity and time invariance, and this is with regard to a particular system. Then we had discussion on LTI, also called linear time invariant systems, which is a very special class of signals that we deal with in this course as well as the future course, most of the future courses, which will have this strong LTI assumption. Then we talk about frequency response, and this specifically can be calculated for linear time invariant systems. And we also talk about the linear constant coefficient differential equation, linear constant coefficient differential equation, LCCDE based representation of such LTI systems. So we first have a brief look at these topics. So the most general way in which we look at signals and systems and this course is this. So we have some input signal which we denote by xt, which gets into a black box and it gets modified to yield some different kind of a signal, which may be something that we want, or this system may be something that we are trying to model. So modeling, in a sense, if you remember our initial discussion in the first week on various kinds of systems, it may be non-electrical systems, biological systems, chemical systems. So we give this the name of a system, and for this course we are dealing with electrical systems. So when we talk about system, a system has various properties to look into, but in this week we are talking about linearity. So what is linearity? So basically linearity is a property that is again constituent of two properties. Okay, let me check whether this recording is taking place or not. Yeah, fine. So linearity is made up of two sub properties. One is superposition and the other one is homogeneity. What does superposition suggest? So let's say you have a signal x1t which you apply to this unknown black box and you get the output y1 of t. The mathematical way of writing this could be t of x1 of t is y1 of t. By t, capital T, I mean that some kind of transformation is being applied on the input signal. Now let's say we apply another signal x2 of t. The system is still the same. We get a response y2 of t, which can be defined as transformation on x2 of t equals y2 of t. Now let's suppose I use the same system. Let me indicate this over here, that all of this represents the same system. Now we add the two signals x1t and x2t and apply to the system. This is the symbol of an adder. And then what will be the resultant if the system is follows superposition? Let the output be yt then it is the same as the transformation of x1t and x2t summation. And if this equals y1t plus y2t, then it implies that the system follows superposition principle. Okay, now let's look. This is all about the superposition. Now let us look into homogeneity. So what is homogeneity suggest? Let's say we look at the same system shown by this black box and I apply the input xt. The output is yt. Now let's say I scale this input xt by a factor alpha and I get the output as y hat t. If y hat t, which is the transformation of alpha xt, turns out to be alpha times yt, that is the output is also scaled by the same factor as the input, then we say that the system follows the principle of homogeneity. Alright, so this is also satisfied. So when both superposition and homogeneity are satisfied, we say that the system is linear. So how can we combine them and answer in one go? So if transformation of x1 of t gives me y1 of t, transformation of x2 of t gives me y2 of t, then if transformation of alpha x1 of t plus beta y1 of t equals alpha y1 t, oops, there is a mistake, slight mistake over here, alpha beta x2 of t, then okay, so t alpha x1 t plus beta x2 t equals alpha y1 plus beta y2 t. If this is satisfied, then we say that our system is linear. So this is the condition that we must check when we want to test the linearity of a system. Okay. So for example, I put forward a system in front of you, a system that satisfies the property yt is 2x of t minus 5 plus 3. Now what does that mean? You give the signal xt, it gets delayed by 5 units, which gives you x of t minus 5, then it gets scaled up by a factor of 2 followed by an addition of a constant term which results in this yt. So you see there are 3 blocks involved in making this system, but what we do is that we don't show all the internal things, we simply try to put them inside a black box and call it a system. Just hold on a second. Okay, so we have to check whether this system satisfies the property of linearity or not. So what I will be doing is checking. Okay, so what we can do, let the input be x1 of t and the transformation of x1 t gives me y1 of t. Alright, that's okay. Now let's say I scale it by a factor alpha x1 t. So I am testing for homogeneity here. Then what will t of alpha x1 t be? So what we need to do is we need to substitute alpha x1 of t into this thing. Okay, so it will become 2 into alpha x1 of t minus 5 plus 3. So what does it become? 2 alpha x1 of t minus 5 plus 3. Let me try to take alpha out, and what do I check? 2x1 of t minus 5 plus 3 upon alpha. And you notice that this is not the scaled version of y1 of t. Alright, so it means that the system is not homogeneous, and if the system is not homogeneous, you can directly conclude that this system is non-linear. Well, a very surprising fact that you might be thinking is that if you look at the powers of, if you look at this term 2x plus 3, it apparently looks linear. Alright, but from a signal system's perspective, we don't have the scaling effect over here. if you scale it by, if you put if you have this x amplified by 2, then the output, because of a constant shift, does not show a scaling by 2. So in that sense the linearity is not there, but otherwise this is actually a linear polynomial. So we should keep this contrast in mind when you are dealing with systems. Similarly we could have also, okay, similarly we can also show that this system also does not satisfy the superposition principle. So I leave that as a homework for you. So that was the linearity. Now we look into time invariance in any system. So what does it mean? Let's say you have a signal xt, okay, it's a triangular pulse, it goes inside our system, a black box, and it gives me some sort of a semicircle, okay. Now what happens when the system is time invariant? Let's say I shift this signal by 2 units of time. So what does it become? X of t minus 2. How does it look like? It starts with 2 and ends at 3. I put it back into the same system and I try to check its output. Let the output be y1 of t, and I observe that the output y1 of t is something like this. Now how do I compare whether it's time invariant? And now let's see, if I have this y of t and I shift it by delta equal to 2, then I get y of t minus 2, which starts at 2 and ends at 3. If these two are equal, then that means that my system is time invariant. Okay, so let me repeat it. A signal xt undergoing transformation gives yt, okay, this is our system's definition. Now shift xt by tau units, x of t minus tau is what we get. Now apply x of t minus tau to system, we get y1 of t is transformation applied on x of t minus tau, okay. Now what we shall do is we shift yt by tau units. What do we get? Y of t minus tau. Now here is a checking point. If y of t minus tau is the same as y1 of t, then system is time invariant, else system is time variant. which means that if you shift the input signal, then the corresponding output is not what you will get by shifting the output by the same amount. Okay, that means that if you shift the input, the output cannot be directly predicted by shifting the previous non shifted versions out. Let me show you an example of such a system. So let us consider the system which follows the relationship yt equal to x of t square. Alright, let my input signal xt be the square wave starting from 0 and ending at 2. Okay, so the resultant transformation applied on x, which means the system output is given by, is x of t. So x of t square, what will it be? Zero to root 2. Okay, why am I saying this? What are the x of, when you're looking at x of t square can be 0 and 2. These are the two critical points corresponding to the starting and ending. So we have t equal to 0 and root 2. We are not taking negative values. The reason being that we are dealing with causal signals, and in our sense it doesn't make sense to put the negative ones. Now let's say I shift this signal by delta equal to 1 unit. So the resultant signal x of t minus 1 becomes 1, starts at 1 and ends at 3. I apply this transformation t of x t minus 1, and what do I get? It starts at 1 and it ends at root 3. But look at this, if I shift y of t by delta equal to 1, what am I supposed to get? It start at 1 and end at root 2 plus 1. So you see, in this case y1 of t and y of t minus delta are not equal. y1 of t is not equal to y of t minus delta. What was y1 of t? y1 of t started at 1 and ends at root 3. What is y of t minus delta? Starts at 1, ends at root 2 plus 1. Okay, so it clearly shows that the system is time variant. So whenever you see some kind of manipulation, so you have, say, let's say any function of t or f of t plus minus k. So these kinds of f of t minus k, okay, where the time variable is not touched upon, we can see that t is not being squared, t is not being multiplied with anything, or there is only a shift plus minus k. So in most of these cases the system becomes time invariant. But if say you touch the time argument like f of 2t, f of sine t, f of t squared plus 3, you try to touch this, you try to manipulate the time variable, then that very moment it becomes a time variant system. Okay, so once when we combine the principles of linearity and time invariance, the system becomes an LTI system, linear time invariant system. So when xt to ht, yt is the output, then okay. So in order to define that characteristic of LTI system, I think you need to wait for next week, because we will learn something called convolution. Or let me state it very briefly, that LTI systems satisfy this property: y of t is minus infinity to infinity of tau x of t minus tau d tau. This is a very significant property of LTI system. We shall not look into this in this week, we shall look into it next week. What is an important thing about LTI system that I can tell you now is that if you apply any complex exponential okay to an LTI system, then the output is also a complex exponential, but the magnitude and the phase changes. Okay, so we say that e to the power j omega naught t, or complex exponentials, are the eigen functions of an LTI system. So what is this eigen function? If you recall your linear algebra course or your matrix algebra course in your first year, then you have learned that if you have matrix A, then any vector x bar that satisfies this property, that when x bar is multiplied by the matrix A undergoes a transformation, then the matrix is only scaled, then such vector x is called the eigen vector, and lambda is the eigenvalue, which means that the shape of the vector has not been distorted, the direction of the vector is still the same. Similarly, in this case, you have a complex exponential, the frequency still remains the same, only the magnitude and phase changes. And so what is the consequence? So in any LTI system, if you give a sine input, then you get a modification in the amplitude as well as the phase. Okay, but what you get is the same frequency sinusoid. Now an interesting thing related to this sinusoidal or this LTI system is the frequency response. What does it mean? Depending on my system's LTI system, the A and phi vary with omega naught. So what does that mean? It means that depending on how fast my signal is moving, my the gain or the change in the amplitude will vary, the phase will also vary. This is called the frequency response. What does that mean? Frequency response tells me how fast or can my system respond to changes. So for example, if I if I give some excitation, or for excitation, let's suppose I wave my hands towards you, you're able to judge me, you're able to receive that signal. Okay, but in case I move my hands too fast, then you are not able to judge that, because the frequency response of your eyes, your optical system cannot accept that frequency. In other words, it does not have the bandwidth. I'm using this term bandwidth to show that how capable your system is in terms of receiving the signals. So frequency response is something, is you have this h of t. So what is this h of t? H of t is something called the impulse response of a system. That means you give delta t as an input, and what you get is the impulse response h of t. Okay, and this h of t, if you take its Fourier transform, you get h of j omega, and we call this the frequency response of the system. Note that h of t exists for all systems, and that's because whenever you give an impulse to any system, you can always note its impulse response. But the frequency response of any is only defined for linear time invariant system. All right. So let us start with some circuits for which we will evaluate the frequency response. We have this capacitor C, and we have this resistance R, and we are taking the output across this resistor. So first, what do we need to find? We need to find the frequency response. How do we write the frequency response? We write the frequency response as the ratio of the output as a function of frequency divided by input as a function of frequency. So what can you see over here? Here you have the capacitance and you have the resistance. We have to find V out divided by V in, which is the voltage divider ratio. So what is the voltage division taking place across? The voltage is divided between the R and the resistor and the capacitor. So we know that for normal any arbitrary resistance, arbitrary impedance, say Z1 and Z2, the voltage output upon voltage input ratio is Z2 by Z1 plus Z2. Now for some of the important this circuit elements, let us write the corresponding impedances. So for a resistor we have R, which does not change with frequency. For an inductance, with an inductor with an inductance L, its impedance is J omega L, and for a capacitor, capacitance C, it has 1 upon J omega C. So what can we write for this C and R? C and R, in write H of J omega. Z2 is R and Z1 is what? 1 upon J omega C. So H of J omega will become R by 1 plus J omega C plus R. Now we multiply the numerator and denominator by J omega C. what do we get? J omega RC by 1 plus J omega RC. Okay, so this is the impulse frequency response of our system. Let's see what we have done the previous week. Have we dealt with anything like this? No, we have not dealt with this in the previous week. I remember having talked about this thing in one lecture at least. Okay, yeah, so we had already discussed this in the week 2, where we had the C and R. Okay, so we have already discussed this, so it's a slight revision. So if we try to see, it has a magnitude component h of j omega. The top magnitude is complex, is imaginary, so we can directly write it omega rc, and the denominator as 1 by omega rc whole square. If we try to plot mod h of j omega as a function of omega, when omega is 0, and it keeps on linearly increasing and it saturates after a point. The point of saturation is the cutoff frequency omega c. Omega c is 1 upon rc. Okay, so what is the behavior of this transfer of this circuit? So you see that it attenuates or provides less emphasis on the lower frequency zones. Lower frequency zones are being provided lesser emphasis compared to the higher frequency zones. So we call this a high pass filter. Another smarter way to judge whether a given circuit is a low pass, high pass, or other circuit is to check the following. So let us know these few things. A capacitor at low frequencies behaves like a open circuit. And at very high frequency it behaves as a short circuit, which is also evident from the impedance. You see Z is inversely proportional to omega, so when your omega is high, your 1 upon omega becomes close to 0. So that means that capacitors, if you know very well, they allow AC currents to flow, but DC is blocked. For inductors at low frequencies, they allow the flow of currents, they behave as short circuit, and I'm sure you have already covered this in your network theorems course. And at high frequencies, because they resist change in current, they behave as open circuits. Alright, so how could we evaluate this circuit? You see, in this C and you have this R. Without even going for any detailed calculation, let us draw the circuit for omega equal to 0 or the DC case. So for omega equal to 0, we know capacitors block DC. So you see VI, there is an open circuit, VO, and you have an R. You see there is a gap over here, which means that VI cannot flow into VO. So VO eventually becomes 0, and this means our low frequencies are not being transmitted properly. So it obviously cannot be a low pass filter. Now you see omega equal to infinity. What happens? The capacitor behaves as a short, and there is resistance. So what do you see over here? VO is directly connected to the input, so VO equal to VI. So it allows the high frequency components to be directly transmitted. So what can we say? It is a high pass filter. So see this very nice trick. Without even evaluating the transfer function, I can say whether the filter behaves as a high pass or a low pass or some others. Let us look at the second example. We have this input, a capacitor, and then an inductor, and then an output. First, let's try to check what kind of a filter it is. Omega equal to 0, capacitors are open, inductors are short. VO is equal to 0 because there's a gap and VO is directly shorted. So low frequencies are not allowed. High frequencies, VI gets directly connected to VO and inductor becomes open circuit. Because of this, VO equals to VI and high frequencies are allowed. So this is our high pass filter. Okay, that's it. Now let us evaluate its transfer function, which will be required in case you have to evaluate its frequency response at certain points. So Z1 is 1 upon j omega c, Z2 is j omega l, h of j omega becomes j omega l by 1 upon j omega c plus j omega l times j omega c 1 plus j omega l j omega c minus omega square lc by 1 minus omega square lc. Omega square you see, even from this behavior you can say that this is also a very okay, there's something interesting going on over here. H of 0 by 0 minus 1, that gives me 0. H of infinity is equal to, so omega square LC, 1 is much, the 1 over here is very negligible when compared with omega square LC when omega tends to infinity, so it is 1. But you look at the denominator, the denominator is omega square LC minus 1. So let us check its zeros. Omega square equals to 1 upon LC, omega equal to 1 upon square root LC. There is a very interesting thing coming out, that the denominator of this the denominator actually turns out to be 0 in one case. So what does that mean? How will h of j omega look like? You have 0, you have 1 upon root LC, So basically we have something called the resonance. The resonance phenomenon is taking place over here, where the gain of the system jumps to infinity. The resonance phenomenon, where upon giving a very slight, if we apply sine t upon root LC, a very small disturbance, then that frequency will get amplified to very high extent. So in other words, if you give a very flat spectrum noise, then this LC circuit can generate a sinusoid of 1 upon root LC angular frequency. So this is actually very common in LC circuits, oscillate, and are actually called oscillator circuits. Now let's look at question number 3. R C, this is the input and this is the output. Let's evaluate it at the DC case or the low frequency case. Vi R, so behaves as DC. At DC the capacitor gets shorted and the inductor is short. VO equal to Vi, so low frequencies are allowed. At omega equal to infinity, Vi still connected to VO via this resistance, and this capacitor gets shorted and the inductor gets opened. So VO is still equal to Vi, so high frequency components are allowed. So that means that the frequency response can have something like this and something like this for the high frequencies. Something must be happening in the middle, otherwise we cannot have a circuit that allows everything going on. So let us, we actually, in for such cases we actually need to check for the possibility. So it is sure it cannot be a low pass filter because it is allowing the lower frequencies. It cannot be a high pass filter, so low pass filter has a profile like this. It cannot be a high pass filter which has profile like this. It cannot be a band pass filter. A band pass filter allows frequencies in between two pass, okay, but it can be a band stop filter. That means it does not allow frequencies in the middle to pass, okay. So I leave this as a homework for you. Okay, no, let me solve it. So what is Z1? Z1 is R, Z2 is 1 upon j omega c plus j omega l, which can be simplified as 1 minus omega square LC by j omega c. H of j omega is Z2 by Z2 plus Z1 omega square LC omega c omega square LC by j omega c plus R turns out to be 1 minus omega square LC by 1 plus j omega RC minus omega square LC. The numerator can be 0. 1 minus omega square LC equals to 0, omega equals to 1 upon root LC. So at this point, it is at this frequency that VO gets shorted to ground at 1 upon root LC. So this is actually a band stop filter. Okay, so I hope now the trick is becoming very clear and you can do this for other circuits as well. Let us now hold the last circuit. Vi, you have R, you have this inductance, and you have this capacitance. Okay, so what is our input? Z1 is R. What is Z2? It's the parallel combination of the inductance and capacitance. Let's evaluate it. Omega L by 1 plus j omega c. So we have L upon c into numerator and 1 minus omega square LC by j omega c. J omega L by 1 minus omega square LC. So h of j omega becomes Z2 by Z2 plus Z1. J omega L minus omega square LC. J omega L by 1 minus omega square LC plus Z1, that's R. J omega L by R minus omega square LCR plus j omega L. J omega L R 1 minus omega square LC plus j omega L. This is our transfer function. Okay, now let's look into the behavior at omega. Okay, omega equal to 0, Vi connected with R via VO, and the capacitor with the inductor over here gets shorted and the capacitor is open, so VO is 0. At high frequencies, Vi is connected to R via O to VO via R, and this is open and this is shorted. Here still VO is equal to O. So low frequency is not allowed, high frequency is not allowed. So it can't be a low pass filter, it can't be a high pass filter, it can't be a band stop filter. The only possibility is band pass filter. So let's look at this. We see 1 minus omega square LC is one component over here. It is 0 at omega equal to 1 upon root LC. So at that h of j omega, we have j omega L by R multiplied by 0 times j omega L, and that's 1. So it's actually behaves something like this. The filter is selective only in choosing the 1 upon root LC. Okay, so you can call this is a very sharp filter. It's not so sharp, but you can change the values of R, C and L to in order to increase the sharpness of this filter. So such filters were used in the very early days in the design of radio receivers, where only a particular frequency corresponding to the channel was tuned, and those knobs which used to rotate were actually a capacitor banks, which when rotated, the overall capacitance used to change, thus changing the tuning frequency. Now let's look into an example through which we will understand the LCC, linear constant coefficient differential equation. If you look at our previous descriptions of systems, how were they? They were something like this: yt equal to 2x of t minus 3 or something of this sort. Now we will show you some systems which are defined by differential equations. In fact, the systems that you can see over here, this inductor, capacitor based, you can also describe them easily using in differential equations by using the KCL and KVL for the capacitors and voltages. So let's look at an LCCD example and you'll solve a question based on that. So for the system with input xt and yt as our output, we have the differential equation: second derivative of y plus 7 times first derivative of y plus 10 times y equals xt. You are given this. Now we have been asked to find impulse response of this system. Okay, how do we do it? Very simple. We have to simply use the concept of Fourier transform, that the nth derivative of the signal is actually j omega whole to the power n x of omega. What can we write over here? J omega whole square y of omega plus 7 j of omega y of omega plus 10 y of omega equals to x of omega minus omega square plus 7 j omega plus 10 times y of omega equals x of omega. H of omega equals y of omega by x of omega. Hmm. 10 minus omega square plus 7j omega. Okay, this is actually the frequency response of the system. So from the differential equation we have reached the frequency response. Now we will look into the impulse response. So let us try to factorize this: minus omega square plus 7j omega plus 10. What can we write? j omega whole square plus 5 j omega plus 2 j omega plus 10. Let us factorize them. J omega plus 5 times j omega plus j omega plus 5 times 2, and that becomes 5 plus j omega by 2 plus j omega. Now we can do a trick over here. If we know partial fractions, multiply by 3 and divide by 3. Why are you doing that? I will show you in a moment. Five plus j omega minus 2 plus j omega. We had to get this into the numerator. Further breaking them down, 1 by 2 plus j omega minus 1 by 5 plus j omega. Now we know that 1 by a plus j omega corresponds to an inverse Fourier transform of e to the power minus at ut. We do this term by term and we get 1 upon 3 e to the power minus 2t minus e to the power minus 5t ut. Okay, this is the impulse response of our system. And how will it look like? At t equal to 0, it's 0, and at t equal to infinity, both the exponentials decay to 0. So it will be something like this. Typical response of a second order system. Alright, now let's look into another question. We are given certain systems, yt equal to 7xt, yt 1 upon 10xt, yt x of 1 upon 2t, t x of t minus 3 equal to x of cosine of t, yt 2 t plus 7. We are supposed to say whether each of them are linear or time invariant. In other words, we are supposed to classify the systems in terms of check the system for their linearity and time invariance properties. So let's number them: 1, 2, 3, 4, 5 and 6. Let's look at number 1, yt equal to 7xt. Linearity, x1 gives me y1 and x2 gives me y2. So y1 is 7x1. I am ignoring the time in brackets and simply writing the coefficients. 1 y2 is 7x2. So now if my input system is alpha x1 plus beta x2, what will y be? 7 times alpha x1 plus beta x2, 7 alpha x1 plus 7 beta x2, alpha times 7x1 beta 7x2 alpha y1 plus beta y2. So the system is linear. If I shift the system x of t by capital T, then y1 of t is 7 times x of t minus capital T. So I substitute this over here, and now if I shift y by t units, it also becomes 7x of t minus capital T. Just try it out once again for your, just try this from your side and you will understand. So for this I actually substitute x of t minus t over here. X of t minus t is substituted over here directly. I mean, I don't put this over here. No, I am putting this entire x of t in over here and getting y1. Fine. Now for y of t minus capital T, I substitute t minus capital T into this argument. There are two different things. One is substituting the entire thing over here, and one is substituting the argument over here. So that's where the confusion lies. So you see, both of them are the same, and hence this is also time invariant. So the system over here is linear and time invariant. Let's look at question number 2. y1 is 1 upon 10x1. Okay, let x1 prime be 5 times x1. What will y1 prime be? 1 upon 10x1 prime, that's 1 by 50x1, and that's not at all 5 times y1. Okay, what did I do? I substituted x1 by x1 prime and I got 15 in denominator, whereas I should have had 5 times 1 upon 10x1. That means I should have had 2 in the denominator, so it's not linear. And if you check it, x1 of t, the argument of t is not touched. Okay, as I had mentioned earlier, that if you see any function where the argument of time is not touched or just added with plus minus k, there is time invariant. So if you verify for yourself, this is actually time invariant. So this is non-linear and time invariant. Now let's look at the third question. Yt is x of 1 upon 2t. You see, t has been messed up over here. T has become in reciprocal. And then what happens if let me demonstrate what I have done over here. X of t minus capital T as yt equals to x of 1 by 2t minus capital T. Okay, that's y1. So what I have done, x of 1 upon 2t has been divided by t. And what is y of t minus capital T? That is x of 1, 2 of t minus t. And both of these are not same, so this is time variant. And if you see here, y is simply proportional to x. Okay, so this is actually linear. This is linear and time variant. Fourth one, you can look into this and without even writing something, you can judge. There is x of t minus 3. Let's suppose you scale xt by 2. Yt will not scale by 2 because you have this minus 3. So this is non-linear because this principle of homogeneity is being violated. Now you see the time index has not been manipulated, so it will be time invariant. You see over here, number 5, yt is x cosine of t. So x is still like a linear term, okay, because y is proportional to x, so it stays linear, and time has been manipulated because of the cosine, so it's time variant. Yt is 2xt plus t, so you can see it's non-linear because you have this plus 7 thing over here, but there is a time invariance because time has not been manipulated with. Okay, so I hope all of what has been taught today is clear to everyone over here, and you will be able to solve the this week's assignment. Thank you.